Good evening, and welcome to the Manning Publications Twitch stream. My name is David Sweet, and tonight I'm going to be talking about practical matters in A/B testing. So these are selected topics from a new book I'm working on with Manning called Tuning Up from A/B Testing to Bayesian Optimization. So now you'll probably be interested in these topics if you are an ML or AI engineer, a quantitative trader, maybe working in HFT, or a software engineer working on the infrastructure for the kinds of systems that ML engineers and quantitative traders work on. So as examples, you might think of a recommender system, like recommending which posts you should see in your stream in Twitter or your news feed on Facebook, or maybe recommending new songs on Spotify. For quantitative traders, create algorithmic trading strategies that trade autonomously, buying and selling stocks or other financial instruments. And software engineers might be looking at an example that I like to keep in mind is an event processing system. So imagine a server that takes in messages one by one from some stream, transforms them somehow, and emits messages. And you might be interested in knowing how quickly that system works, what its latency is. So these are the types of problems and engineers that'll be covered in this talk. Now, just so that we're all, excuse me, we all have the same idea in mind, this is how we'll be thinking about an A/B test for the course of this talk. So you've got some system in production, whether it's a trading strategy or a recommender system, a website, an ad serving system, something like that. Now, A is the current system as it is in production, already running. B is the same system plus some good idea. So imagine you have some idea about how you could improve the performance of this system, and you've implemented it, and now you have a slightly different version of the system, a changed or modified system. And you want to know, is it actually better? Is B actually better than A? Is my good idea really a good one? And so that's where the testing comes in. You run both A and B live in production, exposing real users to your change, or taking real risk with real money in a market, trading stocks, let's say, whatever it is. And you measure the difference in quality between A and B. Does B make more money? Are users more engaged with version B? Do they spend more time on your website, or do they listen to more songs? Whatever it is, whatever your measure of quality is, that's what you'll be measuring in your A/B test. And so here is an unfortunate but empirically true fact that good ideas aren't all that good. Now, for the past 10 years or so, I've taken an informal poll of colleagues in high frequency trading and asked them, how often does a new idea that you have actually pan out and become part of your trading system? And to the person, they've all answered with kind of an air of resignation, 1 in 10. Now, that's not very scientific. That's an informal poll, but there is some better quality data out there. If you look at the slide here, you'll see that Amazon reports 50% of their good ideas after A/B testing become part of the system. They're accepted into the system. In other words, B is better than A 50% of the time. Microsoft, only 1/3 of the time. And Netflix, about 1 in 10, just like my friends in high frequency trading. So why is that? Why is it that these good ideas don't test well? It's not because the people who are coming up with them don't know what they're doing. These are top companies, Amazon, Microsoft, Netflix. So the engineers are smart people who know their products, but they're working on very complex systems. Complex in the sense of the software, the networking, and the people with whom these systems interact. The users themselves are each, you could say, complex systems. And so it's hard to know, hard to predict what's going to happen if you change one of these systems. It's hard to even imagine the entire system. I would say that no engineer working at any of these companies knows entirely how any of these systems work. simply because the systems are too big and too complex. So that's why it pays to A/B test. Now, the domain knowledge that you have, or perhaps any analysis you do offline before running the A/B test, that certainly has value, but it's complementary to an A/B test. It doesn't replace A/B testing. The way I think about it is this. You start out with ideation, step one here, as an engineer, and your idea gets implemented as some change in the system. If it looks good, it's bug-free, passes maybe some software quality tests, then it moves on to step two, where it gets evaluated offline. Evaluated now, not for bugs, but for indications that it could improve the quality of the system, that it could result in more revenue being generated, or users spending more time on your website, or engaging more with its content, whatever your metric is of quality or of business value. In step two, you evaluate that offline. Why? Because it's cheaper, faster to evaluate offline than it is to go into production. But to really know whether it really is going to work well in production, whether this B is going to be better than A, you have to go and do an online test. So that's step three. That's the A/B test. Now, I write it here as measure online because there are other ways to do these kinds of measurements online other than A/B testing. A/B testing is the most popular. It's the simplest. It's robust. It's easy to understand the results and to communicate them to other people. So A/B tests are great. There are ways to do things more efficiently, and they're covered in the book. Various methods are presented of experimental measurement, like A/B testing, including A/B testing, are covered in the book. But in the end, it's this online measurement that determines whether your new idea is accepted into the system or is rejected, and you go back to the drawing board. And this workflow appears in social systems, social media systems, trading systems, anywhere you find ML models or the need or the desire to improve a complex engineered system, you'll find this kind of workflow. So I'm not going to cover, I'm going to give a thorough treatment of A/B tests here, but I do want to just mention some of the basics. Randomization and replication are key to A/B testing. Randomization says, when I take my new idea B, I don't want to expose it inadvertently to, for example, a subset of users that all have some similar characteristic. Like, for example, I don't want to expose my new idea to all people of one gender or all people in one country, or I don't want to expose people to it always in the morning or always in the afternoon. I want to mix it up as much as possible to see whether version B is better than version A across the board in an arbitrary, unbiased way. So randomization is done to reduce bias. Now, replication means running your measurement over and over again. Each time you take a measurement, there'll be some uncertainty in that measurement. And simply repeating the measurement again and again, it will reduce that uncertainty. Or another way to put it is it increases precision. So randomization reduces bias or improves accuracy is another way to say that. And replication increases precision. Now, the way an A/B test is designed, the way you decide how many, for example, how many replications to do, is by a condition where you limit false positives. Typically, they're limited to 5% at most. And you want to limit false negatives. Typically, they're limited to 20%. Now, false positives and false negatives, they mean the following. A false positive would be if you accepted your new idea, but you were wrong to do it, that it was actually a bad idea to accept it. And false negatives, where you have the opposite problem. B is actually a good idea, but you inadvertently reject it. And why would you inadvertently accept or reject? Just due to noise, just due to the uncertainty in the measurements. And so imagine you ran an A/B test every 2 weeks for a year. and you had Microsoft's acceptance rate of 1/3 or 33.3%, you'd find you'd have about less than one false positive in that year and about 2 false negatives. Now that's one false positive. That's in a year. Maybe that's not so bad. I guess it depends, of course, on just how much damage that does to the system. When you accept version B and it's not actually good, when you have a false positive, you're reducing the quality of your system. So it's important to keep false positives out. You'll notice that the false positive rate of 5%, false positive limit, is much lower than the false negative limit. These are typical. You can use other numbers, but these are typical numbers to use. It's because false negatives, when you accidentally don't accept a good quality version B, you pay an opportunity cost. In other words, your system doesn't get better when it could have, but you don't actually do any damage to the system. You aren't reducing the quality of your system. So false positives generally have a tighter limit than false negatives for that reason. Okay, so now, actually I'm going to stop right here for 1 second. This is the end of the introduction to this talk. These are the basics, at least at a shallow level, of A/B testing. If you'd like to understand them in more detail, you can read chapter 2 in the book Tuning Up. But for now, what I'd like to do is go through in each of the slides for the rest of the talk and talk about things you don't normally talk about in an introduction to A/B testing that are beyond just the mathematics and the statistics involved, but rather problems that you run into when implementing these things in a real system, in a real company. And some of the solutions and mitigations that people have come up with that are common across technology and finance industries. So the first problem is this. Imagine you run many A/B tests over, let's say, 6 months. And a common problem is this. I have it actually down here, the second to last bullet. It says net improvement is less than the sum of individual improvements. Now, the problem people run into is they'll improve the quality of their system multiple times through multiple A/B tests over some time period, let's say 6 months. The problem is the total improvement at the end of the 6 months doesn't add up to the sum of the individual improvements. Let's say you ran 10 A/B tests and each of them improved your revenue by $100. At the end of 6 months, you'd expect to have revenue of $1,000 greater, or 10 times $100, than you had at the beginning of that 6 months. What people often see, however, is that that is not the case, that the total improvement is less. And so the first step of the problem like this is simply measuring it. What is the actual total improvement? And that's where the holdout test comes in. What engineering teams will do is take a small sample of their, whether it's users or the stocks they're trading or what have you, however the system is divided up into small units over which they can take measurements. But let's say users. They'll take a small sample of users, set them aside at the beginning of a 6-month period, and those users will not receive any of the version Bs. They will stay on that initial version of the system for the entire 6 months. And then at the end of the 6 months, they can compare that 6-month-old version of the system where you have that small sample of users to the end state after all the A/B tests have been applied, all the acceptances and rejections have been done, and you have a 6-month evolved version of the system. You can compare those two. So you've held out some users. So you run another A/B test on top of everything where A is the system at the start of the 6 months and B is the system at the end of the 6 months. And you ask, how much improvement did we really get? And this is critical in a business because you really need to know how much things are improving. And if they're not, if the 10 A/B tests are not adding up to the improvements of each of the individual A/B tests, you can at least know what to expect from a business perspective in terms of improvement the next 6 months. And you can potentially look for places where there are inefficiencies. Now, why Why don't they add up? Why don't the 10 improvements add up to one big improvement of the same magnitude? One of the reasons is the false positives. You might have measured that B was better than A by $100, but in fact it wasn't. It was worse by $5, or it was just the same as A, or what have you. That's a false positive. So false positives can reduce the net gain over a 6-month period or some other length of time, but let's say 6 months. The other is non-stationarity. The tests you ran at the beginning of 6 months might not apply at the end of the 6 months. Non-stationarity means the system is changing with time. Users are changing their preferences. Traders and markets are changing the way they trade. The signals are changing, or features, let's say, are changing in the quality of their predictiveness. And so that's typical of any engineered system in the real world. It's non-stationary. So those are two reasons why your net improvement over a long period will be less than the sum of the individual improvements. And a hold-up test is key to helping you measure that and set expectations properly. Now, we've been talking here somewhat loosely about measuring the quality of the system. And I've mentioned that the quality of the system might be indicated by the revenue it produces, might be indicated by how much time a user spends scrolling on your app, let's say, or how often a user engages by clicking a like or a heart or retweeting or commenting or playing a song, or maybe showing dislike by skipping a song. Would be a negative reward. Let's say a negative business metric would be that. But the business metric depends on the system at hand. And they're different. There are lots of different types of business metrics. I want to break them down first into timescales. There are metrics that you can measure that give you immediate reward of some sort. There are metrics that are daily aggregates, and I'll give examples of these in the slides that are coming up. And there are business metrics that look at very long-term value. So let's start with the immediate reward. Examples of immediate reward would be the click-through rate. So an action happens, an event happens, a user sees an ad, you show them an ad, and maybe they click on it, maybe they don't, and you know immediately whether that's happened, and that's an entire measurement. You take that entire measurement, log it, and you're done. Another would be something called markout profit in trading. You could imagine you just bought a stock for, let's say, $70. You wait a minute and ask what the price of the stock is. Is it $71 or more? Yes, I've made a profit. Is it $69? I made a loss. But you know immediately whether you've profited or lost. And various engagement metrics, liking, retweeting, commenting, skipping a song, etc. Those are all immediate reward business metrics. Now, what's nice about these can be used for A/B testing. What's nice about them is they can also be used for modeling directly. You can build models using supervised learning methods like regression or classification using logged data straightforwardly. By contrast, the daily aggregates are harder to model in that way. Now, daily aggregate metrics might be revenue for a whole day, or P&L. In trading lingo, P&L is comparable to revenue. It stands for profit and loss over a whole day. Or you might look at trading volume. Sometimes traders have obligations where they need to trade a certain amount of volume during the day. So you might want to measure that. Other daily aggregates might be the time spent on an app. If you're running a website, social media, or running a web app like a social media app, you might be concerned with having users spend more time on your app, so you can show them ads or just simply ultimately show them ads. you want them to be engaged in using your product, otherwise there's no point in building it. Or you might look at the number of songs streamed in a day. You might also just look at active users. For any app or website that has users, they'll typically count the number of people that logged in or viewed pages on their website in a day, number of unique users. in a day. So these are all daily aggregates. These are these offer less data, fewer samples per day than the immediate rewards. You might have, in a large website, you might have hundreds of thousands or millions of clicks in a day, but you only have one revenue number. You might have revenue per user, but even then, each user can click many, many times, but only produce one revenue per day. Now, the final, I want to come back to the daily aggregates in a second, but let's talk about long-term metrics. Even longer-term metrics can be studied, can be measured at a business level and also studied with A/B tests. Like, for example, active users on a monthly level instead of on a daily level. The P&L per trade with a multi-day hold time. You might enter a position on Monday and not close it out until Thursday. Now your rate of new samples, of new measurements, is much lower than if you took P&L per day. An interesting one, if you're writing an ad serving system, you might ask the question, did an ad view lead to a purchase later on? Now that later on could be an hour from now, or an hour from the time the ad was shown. It could be a day later, a week later, a month later. And it's possible to link your view or click to a purchase later on, but it might take a long time for that information to come in. Or you might create an event in your system, like showing users a new type of post. Let's say on Twitter, for example, has Reels now at the top of their feed. If you see certain kinds of Reels or a certain number of Reels that you hadn't seen before, would you be engaged with Twitter more or less over the next week? You might ask questions like that. Now, A/B testing can work on any of these types of rewards, but the sweet spot, I think, is the daily aggregates, because you can't directly model each individual event like you could on that. I'll give an example, the click-through rate. If I show you an ad, I measure whether you clicked it, and I can do that many, many times in a day, and I can write down a model to try to predict whether you would click on it based on features of the ad, for example, and that's done all the time. With the daily aggregates, you don't get enough samples in a day to make a prediction like that, and these daily aggregates tend to be combinations of lots and lots of events or outcomes due to lots and lots and lots of events throughout the day, maybe tens, hundreds, thousands, or millions of events in a single day. So we don't get the option to build a simple supervised learning model that can predict these, at least not in the style of like click-through rates. But you can A/B test these. Now, the way these are preferable to the long-term aggregates for A/B testing is that you get more data. You get one data point per day in these, whereas the long-term ones, you might get one data point over a course of weeks or months. So it's harder to run an A/B test. Not impossible, but harder. So these are this is one of the challenges. This is coming up with a good business metric, choosing the right level of the right time scale where the time is short enough so that you can actually get a good measurement, but long enough that it has a business meaning, and also choosing the quality of the metric in the sense that it should reflect the business needs or business desires of your team for whatever product you're building. Now, in practice, you'll probably have more than one business metric. You'll care about revenue, but you'll also care about how much time a user spends on your site. You might also care about how often a user flags content as objectionable. You might want to reduce that. So in practice, you'll be measuring multiple business metrics, even though in most presentations, including in this book, Tuning Up, of A/B tests, you'll talk about measuring one business metric. In practice, you'll actually measure a lot. You'll measure business metrics you want to improve, business metrics you want to disimprove, numbers you want to increase, numbers you want to decrease, and others that are just constraints or guardrails. You might, for example, want to improve your click-through rate on ads, but only if overall revenue and user engagement with the product don't drop. You're not willing to pay those costs. It's not a trade-off. You just are not willing to lose any engagement for these higher click-through rates. So typically, you'll be looking at multiple metrics for both uh, increase and decrease, and also for constraints or guardrails. So if you've got multiple metrics, how do you make a decision? In a simple presentation of an A/B test, you'll typically look at something like a t-test, maybe a z-score. And you'll say, if my t statistic is greater than, let's say 2, greater than some number, then this is a statistically significant result. But that t statistic will be, I'm not going to cover a t statistic in this talk, but if you're not familiar with it, just know that it is a number that when it's higher indicates, higher than a threshold indicates that you have a statistically significant result, that you've satisfied some condition for willingness to accept B, that B is better than A. But that condition is based on a measurement, typically, of a single metric. What do you do if you have multiple metrics? So in practice, what happens is you have a group discussion and you look at all of the metrics of interest and you look at the uncertainty of those metrics, like or error bars, to answer the question like how clearly do we know this number? If a number, for example, revenue looks higher, but it's a very uncertain number, you wouldn't believe it was higher. So for example, if you're used to making $1,000 a day, you take a measurement that says you're making $1,100 a day. Well, that's better. It's $100 extra dollars. That's 10% more. But if the measurement is $1,100 plus or minus, let's say $400, well, it's unclear whether you're losing $300, right? You're as low as $700, or you're gaining $500. You have a wide range of possibilities when your error bars are large. So you'll look at measured values and you'll look at error bars. And the higher the stakes, typically the larger the discussion you'll have. Larger meaning more people. You want to bring in other teammates. You might want to bring in your manager or a manager's manager. You might also want to bring in other teams. Now, it could be that changes you're making to your product or your trading system or your piece of infrastructure can affect multiple teams. Imagine if you're working on an event processing system, I mentioned as an example for a software engineer, and your event processing system is used by multiple trading groups. If you make a change to that system, and it's a good one, all the trading groups will benefit. But the danger is that you could accept a bad change, have a false positive, and cause harm to all of those groups. So real life decisions typically are more than just looking at a t statistic, but really weighing the risks to the businesses involved and the potential reward of making a change to the system. Now, in these discussions, we talk about the stakes, talk about the risks, talk about the potential rewards, but we'll also talk about domain knowledge. We'll come back to domain knowledge and we'll do sanity checks. If a result looks surprisingly good, you might want to ask, could there be an error in the experiment? Irrespective of anything, your preparation statistics and A/B testing design told you, if it looks too good to be true, it probably is an old saw, but if the measurement is dramatically better, or if it's dramatically worse, but typically if it's dramatically better, that's where you run into problems. You'll need to investigate. Could there be an error in your experiment? Or did you learn something new? It is possible that you've defied your expectations given your domain knowledge and you need to update your domain knowledge, your understanding of the system. But you need to be very careful when you do that. And it might require running more tests, might require testing in different ways, measuring things you hadn't measured before, or just looking more carefully at your code, writing more tests, make sure there isn't a bug. That's quite common. Now, so that's the previous slide was about the end of an A/B test, deciding whether to accept or reject your version B, your new good idea. But there's a whole process before that. Most of the time of an A/B test is spent simply letting it run and collect data, collect measurements, lots and lots of measurements. Now, if you're going to run an A/B test, it means you're deploying new code. That code could have bugs, and so you risk deploying buggy code. And no amount of offline testing, unit testing, integration testing, that kind of thing can tell you that your code is 100% bug free. You, of course, reduce the probability that you have bugs with testing, but once you go online, you can still find new bugs. So that's one of the risks deploying an A/B test. Another risk is the code works fine, but your version B, now we know from earlier slides that typically your good ideas aren't actually going to improve business metrics. And in the worst case, they could reduce business metrics dramatically. And this is the danger of running an A/B test at all, is that you're going to put something new online and it's going to lose a lot of money, or it's going to drive users away. And the effects of changes like that can be dramatic. They could also potentially be long lasting. If you offend users, or if you give them a terrible experience, they might not come back. Some of them might never come back, or some of them might not come back for a long time. And those negative effects will outlast the lifetime of your A/B test. And finally, one of the risks is that you're just wasting time. Right? It takes time to run an A/B test. You'd like to get a good quality answer, and if there's some error in the way the test was set up or the way the code was deployed, that kind of thing, you will have wasted some time. So we want to mitigate these risks. A good procedure for bringing an A/B test online in practice, rather than just turning it on, is to proceed carefully step by step. We'll take as a first step, we'll run a small-sized AA test. And so what is an AA test? This is a tongue-in-cheek kind of engineer joke. The idea is to run your system with all of the A/B testing code required to take measurements, to differentiate between A and B, to do the randomization and the replication, and log all the measurements. Run that code, but in the slot where you would put version B, just put a copy of version A, because you have some confidence version A works. It's been online. It's the current production version of the system. And run it at small size, meaning don't expose lots of users or lots of trades, what have you, to the second A in your AA test. In other words, the A that is playing the role of the experimental version. And if that looks good, and by looking good, meaning you don't detect any bugs, you don't see any dramatic changes in business metrics outside of error bars, then you pass that first test and you move on to the second, which is a small-sized A/B test. Now you do the same thing as the AA test. You keep the number of replications, the number of measurements of B small, or of the experimental version small, but here you're going to use the real experimental version, the version B. You're going to compare A to B. Now you run a greater risk of introducing a bug or reducing business metrics than you did with the AA test. But you see, we're taking baby steps on our way to the full A/B test. If everything looks good within error bars of your business metrics, you'll pass on to the final stage, which is the large-sized or the full-sized A/B test. And now it can run. You'd still monitor it for bugs, for dramatic changes in business metrics that could indicate errors or just a really bad version B, and be willing to take this A/B test offline before it's done if there appear to be any signs of danger. And then in the end, if it runs to completion, you can make your final decision about whether to accept or reject. And we talked a little bit about how to do that by looking at one or more business metrics, having a group discussion, that kind of thing. But those discussions, we'll talk on the next slide, those discussions about whether to accept or reject, they should only be made at the very end. Now, it is not uncommon to say, well, I can measure my T statistic, again, this number that if it's over a threshold, you're inclined to accept version B. I can measure my t-statistic at any time. I don't have to wait until the end of the experiment. So if we, that's a bad idea though. It's called early stopping, and I'll explain why. Let's just describe this graph here that we're looking at. Now on the x-axis, you see n is the index to the individual measurement. So we're going to take lots of measurements. In this case, we just take 100 because we're being descriptive here, trying to teach something, but in practice, you might take thousands, hundreds of thousands, even millions, depending on your business, of these measurements. And now typically, the number of measurements taken will increase as time goes on. You're waiting for users to show up. You're waiting for trades to happen. And you can measure a t-statistic at any point in time. You can ask, is it over the threshold of what's called statistical significance? And I've plotted on this plot in dashed lines the statistical significance threshold, and the solid noisy curve is the t-statistic. You'll notice the t-statistic jumps over the threshold around n equals 18, and then comes back below the threshold around n equals 30. It goes above again, comes back below, and it ends the run below the threshold. Now, with the t-statistic below the threshold, you would not accept version B. But if you had been monitoring the t-statistic throughout the experiment, you might have been tempted around n equals 18, we said, maybe 19, 20, to say, to accept version B, to say, hey, you know what, let's cut this short, let's save time. We don't have to run the other 80 measurements. We can save 80% of the time. We already know the t-statistic is greater than the threshold. Let's accept B and move on with our lives. And this is very common. It's a reasonable intuition, but it's wrong. In fact, doing this kind of early stopping dramatically increases the false positive rate. You can see in this case, had you stopped early around around measurement 20, you would have created a false positive. You would have accepted version B when in fact you should not have. Had you waited till the end of the experiment, you would have rejected version B. The right answer was to reject version B. You would have accepted it in error. Now, just from this graph, it might be difficult to get a sense of how bad this problem is, of just how much you're increasing the false positive rate. But remember, first off, that the t-statistic itself it fluctuates. You can see it fluctuating over the course of this experiment. It's got a little bit of noise to it. It can, if you accept it, anytime it fluctuates, anytime it jumps above that threshold, you're generating a false positive. But there's nothing to offset that. You're either generating a false positive or you're doing nothing. You can only increase the false positive rate. There's no way you decrease it so that your false positives, your increases wash out your decreases. You can only increase this false positive rate. And as an experiment, I ran a bunch of simulated A/B tests. So the capital N on the x-axis, and you'll notice it's logarithmic. There's the numbers at the bottom are 10, 100, 1,000, 10,000, and 100,000 measurements, individual measurements. So I ran experiments at each of these levels. So if you have all the way on the left, if you had only, let's say we go to 10 to the 2, if you only have 100 individual measurements, and you're willing to use that early stopping procedure where you stop as soon as the t-test is larger than the threshold, your false positive rate is going to be around 60%. Now, these are A/B tests designed with the criteria we listed above that limits the false positive rate to 5%. We were very strict about the false positive rate because every time we have a false positive, it means we accept version B when version B actually disimproves the system. It damages the system. It makes it produce less money. It drives away users. Whatever the damage is, whatever the business metric is, it's reducing that business metric. But we think it's going to increase it. That's the false positive. Now that rate, we tried very hard to limit it to 5% by carefully designing an A/B test. But then we went and we used early stopping and we blew it. And the false positive rate went up to 60%, 0.60, when you have 100 individual measurements. In other words, 100 chances to look at that t-test before you were done. If you had 1,000 chances to look at that t-test before you were done, your false positive rate is going to go up to around 70%. If you have 100,000, you're up almost to 85%, all the way to the right, upper right of that graph. So these numbers are so dramatically larger, so much larger, so dramatically larger than the false positive rate you wanted of 5%, that you might as well not even run the experiment. In other words, if you're going to do early stopping, just guess. You'd be better off. You're just wasting time. And again, I've seen this happen many times. It's very common. It is a fine intuition, but if you take the time to look at it carefully, you can realize just how much harm it can cause your system, how much time can be lost, how much money can be lost. So don't do early stopping. And just for the record here, I want to differentiate the term early stopping in A/B testing from the same term early stopping used in neural networks or XGBoost hyperparameter tuning, regularization. The idea there is that early stopping is used to help you regularize a supervised learning fitting process. It has nothing to do with this. It just happens to have the same name. There in neural networks and XGBoost, early stopping is a good thing. Go do it. But here, it means something completely different. Here, it is a bad idea. And I'd advise you to avoid it. I think if you learned, one thing about A/B testing from this talk or even from the book, and it was only this, I'd be happy. It's just that valuable. It's because it's super easy to fix and it can cause a lot of damage. All right, so this one's a little bit more subtle. Again, very common. The idea is this: p-hacking or cherry picking. We've got a false positive rate, and it's similar to early stopping, but it's a different kind of a different way to fool yourself. Let's say you've got a false positive rate. So that means you have a 1 in 20, 5% is 1 in 20, a 1 in 20 chance that when you accept B, you've done so incorrectly. Now, let's say here's where this p-hacking or cherry picking comes into play. I would say typically. Now, we're all human. We love our ideas. Engineers, I find, are very creative, and some of them fall in love with their ideas, and some of them don't. And I don't know what personality trait makes that happen, but it happens. Now, let's say you have an idea and you run an A/B test, and it says reject. I've rejected your idea, and you say, okay, well, you say to yourself, I know this is a good idea. I'm not just going to throw it away. I'm just going to tweak it a little bit, and then I'll run another A/B test. Reject again. Maybe it's not quite right. Maybe it needs another little tweak. I have another idea. I know how to fix this, patch it up. And you run it again. You do this again and again and again. And each time you have a 5% chance of incorrectly accepting this, what is unfortunately a bad idea, an idea that's not going to improve your system. Now, the probability, as you run it again and again, the probability of you not, let's put it this way. I want to say this. I say this exactly. The probability of not accepting this is decreasing exponentially in the number of times you run it. In other words, you're eventually going to accept this thing, even though you're not actually making it any better, because you're trying again and again and again. And one way to look at it is there's a 1 in 20 chance of accepting this thing. I'll run by accident. I'll just run my experiment 20 times, and then one of those times I should expect my experiment to get through the gatekeeper of the A/B testing. But typically in practice, the way it happens is not that you run the same experiment many times, but that you'll tweak it and try again and again and again. And this is dangerous. It's a way to fool yourself, potentially a way to fool other people if you only show them the one experiment where your idea was accepted, and you don't show them any of the results where your idea was rejected the other 19 times, let's say. Another way to get this effect is to look at many metrics. Now, the larger the company, the bigger the product, the higher the stakes, the more metrics you might find that you have. Or just the longer a company's been around, the more metrics they might have, because let's say every few months somebody comes up with a new idea, the metric gets coded up in your A/B testing software, for example, and these metrics accumulate over time. So now, if you measure, let's say 20 metrics, or maybe you measure 50 or 100, but let's say you measure 20 metrics, and they all have some uncertainty, and each one has a 5% chance of showing that your A/B test passed. Well, maybe if you look at all 20, you'll find one that says you did a good job. Maybe you didn't improve revenue, but maybe you did improve engagement. Or maybe you didn't improve revenue or engagement, but you did improve time spent with the app open. Or maybe you didn't improve any of those three things, but you improved some fourth metric. Eventually, if you keep looking eventually and writing down new metrics, eventually you'll find one that just by chance, because of noise in your measurements, shows that you've passed an A/B test. And so both of these things, running an experiment many times or running once and looking at many metrics, are ways to fool yourself into thinking that you've passed an A/B test. Now, why does this work? It works because you designed the A/B test for a single metric run once through one experiment. So you're violating the assumptions of the A/B test design and getting the wrong answer, right? That to put it simply. So this is p-hacking. How do you avoid this though? Well, this is difficult because a lot of what engineering is tweaking and iterating and trying again and trying again. So one practical way to help solve problems like this is when something passes an A/B test, you set it aside and come back to it sometime later and run the A/B test again. And come back to it sometime later and run the A/B test again. As you keep testing and collect more and more statistics at different times with different users and verify that things still work. So holdout test helps with this a little bit because it'll detect whether one of your many A/B tests or one or more of your many A/B tests wasn't as good as you thought was a false positive. So holdout test can help there. With looking at many metrics, there are ways to modify the threshold for the A/B test to account for the fact that you're looking at many metrics. And so that can help. But this is a difficult problem. It is has been a subject of much discussion, even controversy in the past 5 or so years, not just in our engineering fields, but in scientific fields as well. It's non-trivial. All I can tell you is be aware that it's possible if you're running the same or similar experiments over and over again. There's a good chance you're going to get a positive answer eventually, and you should be very critical of that answer. Now, finally, this one's a little bit easier to think about and to mitigate. Transient effects. Now, there's an interesting effect where if you show of novelty, where if you show a new feature, let's say, or a new layout, or what have you, something new in an app to users, they might be interested in it and play with it for a while and then lose interest. Or they might dislike it for a while and then get used to it. Right? So people react to the change as opposed to simply the new level, the new way things are. So transient effects can last, maybe they can last for hours, for days, whatever's right for your system, you'll learn over time by watching experiments. It varies from system to system. But the simple way to deal with this is to throw away the first measurements that you take. Put your A/B test online, let it run for a while, throw away all the measurements you took, and then start taking measurements for your A/B test. Throw away the transient effect. Okay, so those were a few of the topics that are covered in this book. I think a good way to think about how the book is laid out is that time is spent, pages are spent describing or teaching the fundamentals of several experimental optimization methods like A/B testing, but also multi-arm bandits, contextual bandits, Bayesian optimization, and others. So time is spent teaching the fundamentals of these. And that's about 2/3 of the book. And about a third of the book is spent talking about all of the ways in practice that you're violating the assumptions of the fundamentals. In other words, the practical matters in A/B testing and experimentation that will come up as you go into your career, into a company, and put these things into practice. So I hope you enjoyed the talk. I hope you check out the book, and thanks a lot for your time. I'm David Sweet, and the book is Tuning Up from A/B Testing to Bayesian Optimization. Have a good night.